So, probability, what is it? How does it work? Why is it important? How do we determine it? These are some of the questions we're going to answer in this introduction to probability. In considering our first example, it states, a card is drawn from a standard deck of 52 playing cards, and it simply wants to know, what is the probability the 7 of clubs is drawn? Okay, let's see if we can nail this down. Okay, let's get our problem statement down and our expression down for reference. Let me quickly readjust this here. All right. Now for our expression. First thing we're going to do is define our event. All right. So we can see from our problem statement that the probability that we want to determine is the 7 of clubs. All right. So our event is going to be drawing the 7 of clubs. All right. And this is a simple event. All right. As it only has one possible outcome. That is, the only way to draw 7 of clubs is to draw the 7 of clubs. Okay. Therefore, what we can say is that the probability of A is defined as the probability of drawing the 7 of clubs. Okay. And this is going to be equal to, as we can see from our expression, the number of ways that A can occur. Because our event is a simple event, that is, the only way we can draw the 7 of clubs is to draw the 7 of clubs, the number of ways that A can occur will be equal to 1. And as we can determine from our problem statement, the total number of different simple events is going to be equal to the number of cards in the playing deck. Therefore, our total number of simple events will be equal to 52. Therefore, what we can say is that the probability of drawing a 7 of clubs from a standard 52 deck of playing cards is going to be equal to 1 over 52, or 0.019. Let's take a look at our second example. Okay. So here we have our problem statement for our second example, and it states that a 12-sided die with sides numbered 1 through 12 is rolled. Assuming that all sides are equally likely to be rolled, what is the probability that the number rolled is a multiple of 3? Where a multiple is a number that can be divided by another number, in our case, the number 3, without leaving the remainder. Just like in our first example, we'll start by defining our event. Here, we have defined our event as rolling a multiple of 3, which is a compound event. The reason being is that it can occur in multiple possible ways. For example, we can roll a 3, a 6, a 9, or a 12. Therefore, we can define our probabilities as the probability of A being equal to the probability of rolling a multiple of 3, which is equal to the number of different ways that A can occur over the total different number of simple events. The number of different ways A can occur, as we've outlined, can occur by rolling a 3, a 6, a 9, or a 12. Therefore, the total number of ways A can occur is equal to 4. And if you recall, we're rolling a 12-sided die. Therefore, the total number of different simple events will be equal to 12, which simplifies to 1 over 3. Therefore, what we can say is that the probability of rolling a multiple of 3 and rolling a 12-sided die is equal to 1 over 3, or equivalently 0.333. The two examples just outlined illustrate how the classical approach can be used to determine probabilities when the associated events are equally likely to occur. But what about when they're not equally likely to occur? How can we proceed? For that, we can rely on the relative frequency approximation. Here, we have our expression for that, where A, again, denotes our event in question. However, in this case, it represents an event that is not equally likely to occur with other events in the same sample space. Therefore, what we can say is that P of A is equal to the number of times A has occurred divided by the number of times the trial has been repeated. Let's take a look at some examples. In considering our first example, it states, what is the probability that NBA superstar Steph Curry makes a free throw after being fouled? Assume that up until this free throw, he has 5,000 free throw attempts in his career, of which he has made 4,562 of these shots. Okay, let's get our problem statement down. And let me just readjust this a little bit here. Okay. Additionally, we'll get our expression for our relative frequency approximation down for reference. Okay, just like in the classical approach, we'll start by defining our event. And in this case, our event is making the free throw. Therefore, what we can write is that the event A will be equal to making the free throw. Additionally, this event constitutes a simple event, as the only way to make a free throw is to make the free throw. Therefore, our probability is defined as the probability of A is equal to the probability of making the free throw, which is equal to the number of times A has occurred over the number of times the trial was repeated. In this case, the number of times A has occurred are the number of free throws made up until this point, and the number of times the trial has been repeated is equal to the number of free throw attempts, which we can determine from our problem statement. Therefore, we can write the number of free throws made up until this point is 4,562, and the number of free throw attempts is 5,000. On calculation, we get a value that is equal to 0.912. Therefore, the probability that Chef Curry will make this free throw attempt is equal to 0.912, or equivalently 91.2%. Let's take a look at our next example. Okay, do a quick readjust. Okay, our problem states, as of January 2025, there have been 60 U.S. presidential elections. 55 of the winners of these elections also won the popular vote. It wants us to estimate the probability that the winner of the 61st U.S. presidential election in 2028 will also win the popular vote. Just like previously, we'll start by defining our event. Here, our event is winning the popular vote. Therefore, we can write our event A will be equal to winning the popular vote. Additionally, this event is a compound event as it constitutes multiple possible outcomes. That is, there are several ways to win the popular vote, namely by different margins. For example, a candidate could win the popular vote by a margin of, say, 50% to 49%, or a margin of 60 to 40%, or any variation therein. Okay, so our probability can be defined as the probability of A being equal to the probability of winning the popular vote, which is equal to the number of times A has occurred over the number of times the trial was repeated. Our problem statement provides this, as the number of times A has occurred is the number of times a candidate has won an election and also won the popular vote. Therefore, the number of times A has occurred is 55, and the number of times the trial was repeated is the past number of presidential elections, which is 60. Upon calculation, we get a value of 0.916. Therefore, the probability of winning the popular vote after winning the electoral college is 0.916. The two examples just outlined illustrate how the relative frequency approximation can be used to determine probabilities when the associated events are not equally likely to occur. It's important to note that in practice, it's almost certainly the case that the relative frequency approximation will be the approach that is most needed, as events are rarely ever equally likely to occur.